Okay, so we are in generalized linear models with examples in R. We're in chapter 2. We're down on question, what are we on? Question 2.12. Okay, so we are supposed to, in R of course, produce two different vectors of random numbers, 30 random numbers, some for y and some for x, using the rnorm function. Okay. And then we are going to regress y onto x and just simply look at the p-value. Okay. Now, we're actually going to do this many times, so we're going to do it 1,000 times. And we're going to collect the p-value for y on x for each run. Okay. Now, at the end of that, we'll have 1,000 different p-values, each of which coming from a linear regression of y onto x, where y and x are created independently from one another. Okay, right? So y is not going to be defined in terms of x, and x is not going to be defined in terms of y. Okay, and we're going to look at these p-values, and we're going to look at what proportion of them have a p-value of less than 5%, what have a proportion of less than, what proportion is less than 10%. Okay, so let's do that, and then we'll talk a little bit more about it. Okay, so to run this, or to do this, what I'm going to do is I'm going to create this vector called p-values, and I'm going to initialize it just by telling R that it's going to eventually have 1,000 different values in there. But right now, none of the values are assigned anything. They're all in A values. Okay, and then I'm going to run this for loop 1,000 times, and with each loop, I'm going to define x and y, both as being standard normal distributions with 30 observations. Okay, so the rnorm function assumes that you have a mean 0, standard deviation 1, unless you define it otherwise. And so if I just put 30 in there, I'll generate 30 random numbers from a normal distribution. Okay, so then with that data, with each loop, then I will run a model, a linear model that I'll just call M here. And I'm running a slightly different model, just nothing substantial is being changed by this, but by putting the 0 in here, I don't have an intercept, and that just makes indexing the p-value that I want, the one that refers to x onto y, it just makes that easier to access. So that's all I'm doing here. Okay, so I'm going to run this, and again, what I'm going to generate is 1,000 different p-values from 1,000 different data sets wherein x and y are always independent. Okay, so ran that. All right. Now, again, here's the important thing before we start looking at these. The important thing is that x and y are independent. How do we know that they're independent? Because we created the data so that they're independent, right? So we know what the right answer should be here. Okay, that's the important bit here. Okay, so having said that we have made them independent, how many p-values do we expect to be less than 5%? How about less than 10%, or 0.05 and 0.1? Okay, so maybe take a second to try to answer that for yourself, or make a guess. All right. So to answer, well, for me to put my answer out there, okay, remember what p-values represent. They represent the probability of our null distribution generating the data like what we found. Okay, so we should expect about 5% of our p-values to be less than 0.05 and about 10% to be less than or equal to 0.1. All right. So let's look at what we got. So I'm going to run a histogram here with 20 breaks, and so that should put a break at 0.05 and 0.1 and 0.15 and 0.2 and so forth. And then I will demarcate, p-values less than 0.05 and 0.1. But then I will also, within our vector of p-values that we generated, I will count how many are less than 0.05 or 0.1 and then divide by the length. And so that will give us the percentage that are below 0.05 and below 0.1. Okay, so running this, okay. So here we have the distribution of our p-values, right? And it's more or less uniform, which is correct, right? There's some sampling variation in there, okay? But we notice that there's a sizable number that are, less than 0.05 or less than 0.1. Okay, and that's to be expected. Okay, so what's the lesson here? So I don't know what the lesson is, but there's a few lessons, and I'm probably leaving some out. Okay, but maybe the first one is that null hypothesis significance tests, which is what we've done when we're looking for the p-values, they do not test the experimental hypothesis, but rather they're testing the null hypothesis. Okay, so that's important to keep in mind. Okay, another thing here is that when we have a rejected null hypothesis, in other words, we would maybe be encouraged to accept the alternative hypothesis. It remains contentious for a while. Okay, just because we reject a null hypothesis does not. We should continue to be suspicious of it. Okay, so to properly test a hypothesis, so a non-null hypothesis, the interesting hypothesis, we need to make sure that we have many controls in place, or all of the right controls, and that the result gets replicated several times, and that the hypothesis is being tested in several ways, and it's being tested in several contexts. In other words, by different people, equipment, different location, etc. I accidentally put 4.2 here, but number 3 is if we run a large number of null hypothesis significance tests, we will lead to false null hypothesis rejections, right? In other words, we are going to be embracing many incorrect hypotheses, okay? How many? Well, about 5 to 10%. That's under ideal circumstances, okay? So between 5 and 10%, depending on what your level of significance is, okay? So under ideal circumstances where you've perfectly conducted your experiment and so on and so forth, and you weren't dishonest, or you didn't do anything that may be incidentally biased, what you've done, you still expect 5% or whatever your p-value is to be incorrect, okay, to be false. So anyway, I guess we will leave that one here.